Welcome to my talk on the 4 GB by 4 GB VM split. This is something that has been coming for a while, and we haven't really started working on it, but we have a plan. To explain really what we're doing here, I'm taking a big step back and just explain how monolithic kernels work in general, and then we'll go from there. So in an operating system like Linux, we have user processes that are strictly isolated from one another, and they each have their own address space and their own resources that are all virtualized. And then we have the kernel, which has everything shared. So everything the kernel does on its own is shared no matter what process you are running on. So the kernel has the same view of memory, whatever process is running, and it can see its own memory, and it can see the user's memory, but the user cannot see the kernel's memory. Okay. So whenever something happens that either is triggered by the application doing something intentionally or unintentionally, or by the hardware that requires the kernel's attention, we change state from unprivileged to privileged, and then execute in memory that is only visible to the kernel. And whenever the kernel is done with it, it just returns to user space. And that user space could be a different task, in which case we have had a task switch or process switch. What this means on Linux on ARM, this is the generic memory map that you would see on a lot of architectures, but not all of them. So usually, as it is on ARM, we have the user space see its own memory at low addresses. So anything up to task size is user addressable memory virtualized, and anything above it is only visible to the kernel. And then above task size, we have two main areas. One of them is linear mapping of physical memory, and the other one is what we call the vmalloc zone, where we put everything else that is accessed, that is mapped dynamically at runtime. So that could be loadable modules, or it could be large allocations of non-contiguous memory, anything like that. And then there's something called Highmem. What it means to have Highmem on a 32-bit machine, this physical lowmem area is typically only 768 megabytes in size. So that's as much physical memory as you can map into this red lowmem area. And if you have more than this, the rest becomes Highmem. And a user process has a random mapping of physical pages, 4 kilobyte pages, between the physical address on the right and the virtual address on the left. But in kernel space, only the lowmem is mapped. So if we want to access Highmem pages from the kernel, we have to map them into the vmalloc area dynamically, do whatever action we need to do, and then unmap them again to get the space back, because we can't map at all. That's the whole point. Highmem is a huge problem for a number of reasons. So just this week, there's another discussion about what can we do about Highmem, because it's so annoying to have to go and map one page at a time when we want to access it, which has all kinds of implications. So Thomas Gleixner posted a patch series to fix some of the problems that we have with Highmem, but he also said like the only real solution is to remove it completely. And the patch series has gone back and forth. We still don't have a solution for the particular problem they were trying to solve. And this has been going on for a while. There are two interesting articles on LWN that you can read about it. One is a story from earlier this year, where we first discussed like how long do we still need to have Highmem? Can we remove it now? Can we remove it later? Why should we remove it, or what needs to be done? And the other story is about the recent development where one of the solutions is to make it a little bit slower but less annoying. There's another solution that you can do on a particular system. The boundary between user memory and lowmem is actually configurable at compile time of the kernel. So you can compile the kernel to have, let's say, 1 GB of lowmem instead of 768 megabytes, or you can have it, in the extreme case, set to 2.75 gigabytes. But that means you only have 1 gigabyte of virtual addresses for user space, and that is a huge limitation for some processes. Like a lot of applications wouldn't ever notice because they run fine within 1 gigabyte. But another LWN article that I'm citing here that you can read up on is a description of what goes wrong with the current 3 gigabyte limit. So there are already tasks that fail because they run out of virtual addresses, even if you have a lot of physical memory still available. So reducing it to less than 3 gigabytes means that more applications will run into this particular problem. Ideally, we would make it larger. And on a 64-bit kernel, you can actually use the full 4 gigabytes of address space for user space. So this is the idea that we've had for how we can solve this problem by introducing a number of others. So rather than having multiple processes at low addresses and then a little bit of physical lowmem, we would have a fairly large amount of lowmem and a fairly large amount of address space for user space, but only have one of them at a time, and then we switch back and forth between them. So just like we switch between user processes, we now also have to switch to the kernel. This means we can still have Highmem, but in all systems that have less than 3.75 gigabytes of RAM, we wouldn't need Highmem. If we do have Highmem, then the lowmem becomes much larger, and we would still have to map Highmem pages into the vmalloc area. So how often is that the case? I took a very unscientific look at what kind of machines people actually use on 32-bit ARM. In a talk I gave at the last Connect, I talked about how many machines are actually still in use with 32-bit ARM, and it's about half of the ones that we get patches for in the ARM SOC tree. But it turns out that most of them don't actually have more than 1 gigabyte of memory. So only the ones on the right of the screen are actually affected. So these are the ones that use some amount of Highmem, and everything to the left doesn't, as long as we make the VM split so that a whole gigabyte can be mapped. The 1 gigabyte case is extremely popular. The 2 gigabyte case is not quite popular because a lot of the machines with 2 gigabyte and more are already running 64-bit kernels. In that case, we don't have a problem here. And this is actually a trend that I expect to continue. Just because at 2 gigabytes, it's often cheaper to get a 64-bit system with LPDDR4 memory than have a 32-bit system with DDR3 memory and have 4 chips at the same time. So this is what I expect 32-bit systems to look like in the long run. We'll have something like a Cortex-A7. Most likely, a lot of these systems will actually use a Cortex-A7. 512 megabytes of DDR3 memory is kind of the sweet spot because that is the largest chip that is in mass production that you would use on such a system. If you get to larger memory, you need more chips. And that makes a more expensive board design. At some point, you get into the area where running 64-bit, again, is cheaper. And anything other than DDR3, so the older technologies, are already kind of obsolete because you can't save much money by using DDR1 memory instead of DDR3. The only reason you would do it is because you have picked a chip that does not have DDR3. Then you might have 64-bit hardware, in which case I would just strongly recommend to run a 64-bit kernel. As I said, with a 64-bit kernel, you don't have any of these problems. There's no Highmem, and you might still want to run 32-bit user space, especially if you have less than 2 GB of RAM. It makes sense because 32-bit user space, by definition, uses less memory. It has smaller pointers, smaller long variables, and you can also use thumb2 instructions to have a smaller iCache. So how do we actually implement it on the machines that we still care about, that are running 2 GB of lowmem and will have to support for a while? There are two different classes of machines that are still popular today. There's the classic, which is anything before ARMv7 plus the Cortex-A8, A9, and A5. And then there's the modern cores, ARMv7VE, which is Cortex-A7, A15, A17, and a couple of others, and anything ARMv8 and higher. So as I said, 4 GB is already fairly uncommon, but there are important systems that use it, and there are even some systems with 8 GB that we will still have to support at least for another few years before the existing users move off of them. On older cores, it's exceptional to have an ARM11 with 1 GB, although that does happen. And on a Cortex-A9, 2 GB is already rare, and 4 GB is the absolute exception. Yes, there are those systems, but they are in very small numbers. So maybe you can wait for them to all fall out of use. The most important exception is the IMX6 Quad and Quad Plus that has a Cortex-A9. It does not have a modern MMU with LPAE, but some people have shipped them in the past with 4 GB. So this is the timeline that I can imagine for what we would do. We would introduce the VM split 4 gig option that I've briefly shown. We would make it the default, which means that any system using 3.75 GB of RAM would not use Highmem at all. But systems that do use Highmem, systems that do have more than 4 GB, they would still be able to use Highmem until we have determined that all of these systems have fallen out of use, and at that point we can drop Highmem support. And for the older kernels, for the older hardware, I would like to add the 2 gig opt option, which means we allow exactly 2 GB of RAM to be accessed without having Highmem, because currently if you have the 2 gig memory split, you get slightly under 2 GB of memory and then a little bit of Highmem, which is almost as nasty as having a lot of Highmem. And then equally, we would keep using Highmem for some systems, but eventually drop it when we are fairly certain that the existing users do not care anymore. And in both cases, I do not expect to see any new users. So this would be the Highmem system in those two cases would be for users of existing hardware. So back to the implementation. So there was actually a VM split 4 gig option for x86 some 18 years ago, when there were still large NUMA systems with something like 16 discrete CPUs on x86-32. And they could address tons of Highmem. And there was a patch to make the lowmem larger while still having Highmem. And it was fairly expensive, and it was ugly, and that is the reason it never got merged. So the baseline is we have to be better than that to even have a chance of getting it merged. So this was shipped in Red Hat Enterprise Linux at the time, and then it completely fell out of use. With the ARM v7, with the LPAE MMU, there are a couple of tricks that we can do that help us. We have 2 page table base registers. That is, unlike x86, we can change the address spaces for high addresses and low addresses separately. We have address space identifiers that mean we do not have to flush TLBs, which was some of the where the largest overhead came from in the old approach. And the MMU is flexible enough that we can pick any ratio between the upper and the higher, the upper and the lower page tables within certain bounds. So the minimum size for one of the page tables is 1/4 GB of memory, and there's that's where this came from. That I said we would keep the vmalloc area of 256 megabytes permanently mapped. There are 2 problems with this. The first one is how we do the exception entry and exit, and the other one is how we access user space memory when we are in kernel and user space has been unmapped. So for the exception entry, at the moment the kernel runs actually in the linear mapping, and when that is going away, we cannot just jump into the kernel at the time an exception happens. And for x86, the approach was that there's a small trampoline, like just a little 1 or 2 pages at the top of the address space that hold a little trampoline. All the exceptions would end up in that trampoline, then swap the page tables, and then start executing the normal kernel. But what I think would be better for a number of reasons here is to have the vmalloc space permanently mapped. User space would still not be able to access it, just as it isn't now. But it would be there, and all the exceptions could just point in there, and we need to move the kernel into it. The kernel is around 20 megabytes typically on the 32-bit system, so that easily fits. It's maybe 10% of the available address space. We could also map the kernel stack into the same vmalloc area, which we currently don't. So this is something we have to decide at some point, and we'll see later why. We would have to reserve 1 address space identifier, and the address space switch just happens whenever we enter the kernel. So all the kernel code is already mapped, so we can use the existing entry code. We just reload the page table base register when entering the kernel. And we actually have an early prototype of this that Afzal Mohammed has implemented. But there's more work that needs to be done on this. The other problem that I mentioned is accessing user memory. So this is something that you do whenever there's a system call that passes arguments outside of registers. So if you call the root system call, the kernel would operate on a file descriptor, get the data, and then it would call copy to user to actually copy the resulting data into the target address. At that point, you need to have access to user space memory. And all the existing code wouldn't work, so we have to rewrite it somehow. Unfortunately, none of those options that we have come up so far with are really nice, but I'll show you anyway what we have. So the first one would be what the existing x86 method does. And again, we have a prototype for this, but it turned out to be really, really slow. The idea is that we do the same thing as the hardware. We walk the page table. There's a function called getUserPages that we can use to map, to find out where in the physical memory this is. Then if it's actually a Highmem page, we map it dynamically, otherwise it's already mapped. Once that page is mapped, we just do a memcpy. It won't fault, and the data is there, then we unmap it, and we might have to do this for one page at a time. For if there's a large read system call or something other, then that takes a lot of data. And nobody really likes this approach, but it is actually possible to implement this in an architecture-independent way, and it's a good baseline, so we might keep this. The second one is the get user, put user functions are optimized versions of copy from user, copy to user, and they just read or write one register. So what we can do here is, since the code is already in vmalloc space, it won't go away. We flip the page table, we do the access to the user pointer, and then we flip the page table back. The overhead isn't quite as bad if you're just reading one word as with the other approach. But you still have to load, you have to store that page table base register and then have a barrier. So there's a significant overhead still, especially if you want to do this for a large copy rather than just one word. So the next trick would be to do exactly the same, but do it for multiple registers. If the memory is aligned, we can just do load multiple, store multiple, and do 32 bytes at a time, which is something. Approach number 4 would be to use all the registers we have available, including the neon registers. And the neon registers give us 256 bytes, so we could do a copy of a whole page by flipping back and forth 16 times, which is still expensive, but it might just be good enough for large copies. Another approach is, rather than having mapping the user space into kernel, we just map the linear page to a different location in the vmalloc area, and then do a memcpy there, which is a little bit cheaper than mapping user space, but we still have to update the page tables and flush at least one TLB locally, and we'd still have the reload of the base register. And then one more idea, if we have the vmalloc stacks that I mentioned earlier, so all the per thread stack memory is also part of the vmalloc area, then we can have an even larger area. We don't have to save and restore the neon registers, but we could have, for example, 1 kilobyte of stack space that we reserve for this purpose. So anytime we do a copy from user, we would put an array of 1 kilobyte on the kernel stack, flip the page table, and then do a memcpy between that. The disadvantage is we have to do the memcpy twice, and it's still not that much memory that we can copy at once. So for which of those 6 approaches we'll actually take, I think we'll have to probably try them out all. We'll have to see how expensive it is to flip the page tables, and then come up with a good combination of the approaches that work best depending on the particular size of the copy. There are possible other benefits besides avoiding Highmem and giving more address space. We have the privileged access never feature on modern 64-bit CPUs, and we have software implementations for both Arm v8.0 and for anything that does not run the LPAE kernel. We can emulate the behavior where we prevent the kernel from accessing user space other than with the get user, put user functions. And if you want to know more about that, there's a good link that I put in again. But with the proposed approach, we would get this also on LPAE. Basically, it's the same feature. Another implication would be that it is kind of similar to the page table isolation, that we have on 64-bit architectures, it doesn't give you the whole isolation. So user space, if there's a CPU with a bug that lets you bypass the page protections, like the Meltdown bug did on certain CPUs. The idea is that by isolating the page tables, the kernel would just not be mapped, and you can't gain knowledge about what's going on in the kernel. With this approach, we would prevent user space from accessing the linear map, but we do not prevent it from accessing the vmalloc space. So it's like halfway there. I also looked at what we can do for other 32-bit architectures, just because the question is, how long will we need to keep Highmem around? If we can't get rid of Highmem ever, then this is all not that interesting. But if nobody else uses Highmem and arm32 is the only thing that's still interested in it, then it becomes very important to do this. It turned out that most architectures are in a similar situation, and most 32-bit architectures are actually not used as much as arm32. So MIPS is probably the one that is most affected. There are two SoC families that people are still actively work on in the kernel that have this problem. So the Baikal T1 SoC was just merged into the MIPS kernel, and they run up to 8 GB, but can only have half a gigabyte of lowmem. So they certainly have this problem. They could use the same approach to get maybe up to 3 GB, just because the MIPS architecture is a bit different. For the Unchecked chips, they are in some of the very cheap devices, but the ones that actually have 1 GB are no longer being marketed. So these might go away around the same time as the last ARM systems that have more than 4 GB. For x86, as I said, there were large NUMA systems in the past, but they are basically all gone now. And the only things that I found that would be relevant for x86 are round about 2006 to 2008 era netbooks and 32-bit laptops that have up to 3 GB. And they could use a VM split for 3 GB, but it is, if anybody still uses those laptops, they have a problem. And then there's an embedded system called the Vertex 86EX2 that can address up to 2 GB of physical memory. And that is actually still being marketed today, and they come out with new versions. So they would also have a problem there. On PowerPC, most of the systems are fairly old too. The PowerBook laptops are in a similar situation to the x86 laptops. And then NXP has a couple of SoCs that are also getting old by now that can address up to 8 GB of memory on a 32-bit CPU. I couldn't really find out anything about the other architectures that I've listed, but those are all the ones that use Highmem today. And that's it from me. I see there are a couple of questions. So Art says that AH32 only has 16 Neon registers. Yes, that is true. But I think that the 256 bytes was correct, right? Is it possible to do DMA in place of memcpy is another question. If you want to do DMA, you still have to know the physical address. So what makes the approach that I mentioned expensive with the user memory access is mostly finding the page and making sure it doesn't go away. So if you want to do DMA, you have almost the same overhead, and then you additionally have the overhead of starting the DMA and waiting for it. So this wouldn't be any faster. Another question, when we are using the option, is kernel helper function mapping to the same vmalloc area? In this case, is the vmalloc space too small? My expectation is that 256 megabytes of vmalloc area is sufficient. If it's not sufficient, we can double the size. Like we can go in any power of 2. So it could be 256 megabytes, 512, or 1 gigabyte, which in turn means we have less lowmem. But that is currently the trade-off. I think that the 256 megabytes should in general be enough. And the VDSO is actually part of the user mapping. What's the time? Okay. I think we're out of time anyway.
So there is a Slack channel, so people can carry on the conversation in Slack. There is a question from Dan Thompson in the Slack channel already.
Okay. I'll go into the Slack channel then. Thank you, everybody, for listening.